So this is the third in my Let's Learn, Let's Code series. The first two were based around how to do NTSC video output using an AVR. Both the basics, right here if you want to click on it to go check it out, and chroma, how to actually encode chroma into a signal without any real special hardware, just an AVR. So if you're interested in either of these, you can click them now. Otherwise, we're going to go on with the capacitive touch sensors. These are the same sort of touch sensors that I've used in a number of projects, including the MagFest badges, what we're actually going to be using to set all this up. If you want, you can click right there, as well as a number of other projects, and even this is the same sort of system I used in order to do my glass circuit boards that are touch sensitive. If you're curious about that, you can click right here. Okay, so the basics are you have a finger and you have a sensor, and you want to know if the finger is touching the sensor, and we're going to have some magic. This is what we're going to talk about, and what we're going to, well, by the end of this, if you have some experience with AVRs, you may even be able to go do this magic yourself. So let's see, what are the different forms of touch sensors? So we have resistance based, which means that you have two terminals, and if there's resistance between the two terminals, then all of a sudden, blammo, you know that somebody's touching it. These aren't really that popular anymore, mostly because capacitive is just so gosh darn easy, and they have certain problems detecting in noisy environments. So your finger does have resistance to it, and you would be able to detect it just by looking at the resistance between these two. You can see that most notably if you use, say, a voltmeter and hook it, or ohm meter, and hook it across 2 points on your skin. You'll see that there is some resistance. Another kind is a resistive touchscreen sort of thing, and that's totally outside the scope of what we're dealing with here, but it has to do with measuring the resistance across a film and being able to locate a point of contact on that. Another one is contact. So this is very similar to the capacitive insofar as only needing to have basically one terminal that makes the contact you need. And this one terminal will be able to detect it. So when you touch it, you complete a circuit, and you basically become an antenna, and whatever's on this other side is waiting for the signal to get really strong. But the part that I'm going to be talking about mostly here is capacitive. And it's because for what I do, it's the most useful, and it's very simple to implement on an AVR. So, blammo, we're doing that one. So, let's see, what exactly is the general idea of what we're talking about? Say we have a capacitor sensor, and it hooks up to nothing. Well, then it's going to say there's no capacitance there because there's nothing on the other end of that sensor. And it knows that, that's simple. But what if we do put a capacitor on the other end of the sensor? What if we have this 100 picofarad capacitor right here, and we hook it up to our cap sensor? Well, nothing, because the other side of that capacitor is disconnected. It's as though this capacitor doesn't exist at all. But if we hook up, say, the other end of the sensor and complete the circuit ground here, now all of a sudden our cap sensor can tell exactly what capacitance this capacitor really is. So how does this work? Well, you are the ground. So if we have a capacitor and you touch the other side, you basically complete that circuit there. Now, you're not entirely the ground, but we'll get into that in a little bit. So these capacitors, how do they work? Well, you have two conductors, and you have an insulating material, a dielectric in between, and you have another conductor on the other side. So this would be a plate, a couple square inches by a couple square inches, and this one here will be another plate, which is a couple square inches. Then if we want to measure the capacitance across here, we can just put it ground around to cap sensor, and we can tell what the capacitance is across these two plates. Well, if you have two plates this far apart, the capacitance is going to be almost non-existent. So what we'll typically do is we'll have that be a very thin gap between these two plates, and now we have a much higher capacitance. The physics behind that is totally outside of the scope of this lesson. And we say, well, what about if we just short it? We should be able to tell, yeah, well, that doesn't really work because you aren't actually ground. It's a little complicated. You basically act like a ground because your body can hold a charge. Well, I say charge, but what exactly does this charge have to do with capacitors? Well, say we have a circuit here. We have a switch that we can turn on, and we have a capacitor and a resistor. And capacitors resist change in voltage, so they can store up voltage over time, slowly gaining, and now they have voltage in current. They have energy stored inside of them. which will create a potential across them. So say this terminal right here could be 5 volts, and this terminal here could be 0 volts, and the voltage across the capacitor is, say, 5 volts. If you have a capacitor sitting in the middle of nowhere, it's going to just maintain that charge for a very long time. I actually opened up a package once that contained 2 very large capacitors, and I didn't bother checking to see if they had any voltage on them to begin with, and sure enough, even though they'd been shipped to me and over the course of several months, they retained their charge. So for what we're doing, we're going to have a resistor here, and it's going to deplete the charge in this capacitor. So initially it's going to start off with 0 volts, like that. If we lock the switch down, then this 12 volts will flow into this capacitor and charge it to 12 volts. Then, if we let go of that switch, then naturally the resistor is going to be depleting the charge in the capacitor, and so the voltage will drift down to 0. But you say, well, what if there was no capacitor? Or what if the person wasn't touching it, or whatever? Well, if we have a switch, there's nothing charging here. So if I turn it on, it'll go to 12 volts, but it'll immediately fall off. In reality, it doesn't immediately fall off because there is residual capacitance here and all sorts of other things, but it's night and day. It's orders of magnitude sharper of a slope. So it's pretty easy to tell whether or not there's a capacitor just by looking at that curve. Now, you say, okay, that's great and all. It's a little bit difficult to do it that way on an AVR though. So one thing to take note of is we can do it entirely the other way. We can flip it upside down. We can say have 5 volts being what the resistor is charged to. So naturally, the capacitor and resistor circuit there is going to want to be at 5 volts. Then we can use a switch in order to turn it off effectively, or I guess short it to ground. So now all of a sudden it's 0 volts being read right here. Then over the next couple seconds after we release, it's going to slowly rise back to 5 volts. Once it hits this threshold here, we can then mark it. So immediately after we turn off the switch, we can start a stopwatch, and then we can measure that delay. So really the fundamental thing that's going on here is the more area, and the closer you get 2 sides of a capacitor together, the more capacitance it has. So what that means is, when you have one plate, and you have your thumb now completes a capacitor. Your thumb is the other side of the capacitor. Your thumb doesn't have very much surface area, and it doesn't have to be that close, but it's because we don't need much capacitance. Then, the more capacitance we have, the longer the delay. So if you don't have your thumb on the circuit at all, and the capacitor barely exists, it's going to be a very sharp edge there. So the delay is going to be very small. If you put a lot of surface area of your thumb on there, say, then that delay is going to be much longer. And we can use the timers on an AVR to figure out exactly how long that would be. So let's go take a look at what this sort of thing looks like in an oscilloscope. So here on the oscilloscope I have basically what I showed you guys before in that schematic. And on the oscilloscope it basically sits right here, and then it turns on the latch. So it drives it low, as I showed you in the second schematic, and then it lets go. So the voltage rises up because there's a 1 mega ohm resistor pulling the voltage to 5 volts. It chills there for a long time until, again, I draw it low. And let's go take a look at the code here. So in the code, really, this is very simple. We're just doing some basic things here. We're setting up a clock so that we go at about 14 megahertz. We set up the SPI, make it so that the SPI can talk by debug mode so that we can get printing. And we're not going to be setting up any timers right now, but we will be doing 2 other things. One is setting up a marker right here, and that's to make it so that we can sync the oscilloscope to our clock. So, over on the oscilloscope, if we look at channel 1, we actually have this nice little square wave. This is being generated as a marker so that the oscilloscope can latch on to something to be able to keep this waveform nicely in sync. So, back over here, we're going to be saying that port B3, which is the pin that this pad right here is hooked up to. Well, that should always be driven low. Well, not necessarily driven, but it should always be low. So if we're driving it, we'd be driving it low. So back over here in the code, what I'll do is I'll say it's just low. Now I'm not driving it yet, but it's low. I'm also just sending string mark just to make sure that you know, the code is working and awake and everything's fine and the debug link is good. So right here, I lock the port down, and that's this point on the oscilloscope right here. We're right now activating this, and it's being driven low. So this is now at 0 volts. And if we go here, we can see that I'm also marking it so that the oscilloscope can lock onto it. Everything's fine. We wait 1 full millisecond. So between there and there is 1 full millisecond. Then we release the port, and then we mark it on the oscilloscope. But we release the port there, and we wait another millisecond. So you can see this is 1 millisecond, and this is 1 millisecond. Now, here's the interesting part. I'm completing a capacitor. Right here, this pad underneath is one side of the capacitor. My thumb is the other side of the capacitor. And this blue material here, this is, I believe, enamel, it's just the solder mask, is the dielectric. So, as you can see, the voltage rises very quickly. But when I put my thumb down, the voltage rises much more slowly. So say that this marker right here, let's see if we can zoom in. Say that this marker right here is the threshold. I don't actually know what the threshold is on the AVR for logical 1, but let's just assume that it's that marker right there. Right now, it crosses right there, which is very, very soon after it was released. But if I press down, it crosses much later. So now, it's basically 2 to 3, maybe many more times longer. And that's how I can tell how hard a person is pressing, or if they're pressing at all. So just by pressing, as you can see here, I'm just taking my thumb and going boop, 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 and it's clicking and clicking, and by doing that, we now have an electrical response that we can take a look at. That's not all that interesting though, because I have to have an oscilloscope to tell if I'm pressing. So how would we go about this in code? Well, it's not that bad. Really, all we have to do is set up a timer. And this time I'm going to be using timer 1, which is an 8-bit timer on this ATtiny85 that's running on the MagFest badge there. Which, by the way, if you're curious, you can click on the video about the MagFest badge right here. Okay. Anyway, the idea is that we want to set up a timer, and we're going to do that. We're going to say I want to do it at divisor 1 and divisor 2. I don't remember what that works out to be. It's something like probably 1/64th the clock rate. And I want to turn on sleeping, and I want to enable pin change interrupts. That pin change interrupts is a pretty big deal right now, and you'll see why in just a minute. So, like before, we'll still want to lock the port down. We'll still want to have a marker, but instead of delaying a millisecond, you can just print something. So let's say I have a local variable j. I'll just print that. Send hex to j. Okay, so right now, let's make sure that that works. Ooh, terminal does not like that. Okay, let's try making it and running it. So now, oh, that's confusing. Hold on, let me go fix that. We actually want to send a new line. So send chur, new line. Let's try that again. Ah, okay, excellent. So j has 0 in it. Everything is fine. And let's zoom out on the scope. Sure, it looks like we're still able to track onto everything and has a nice, still good curve to it, so we're good there. Now, the next thing we're going to need to have is an interrupt. We're going to use this interrupt right here. I'm not actually using this part yet, but the idea is that whenever this pin changes, we're going to call this interrupt, and we're going to set TR to be TCNT1. So that's important because I'm going to go put this code in right here. Actually, I'm going to go put this code in right here. So, like before, we release the port and we set the marker on the oscilloscope. But here we do something a little bit different. We reset the timer. So setting it to 0 says start. Effectively, like you just reset your stopwatch and you're going to start it now. Or it's always running, but now hit reset. Doesn't really matter how you think about it. Now, I also set TIFR to be OCF1A. Actually, don't need to do that quite yet. Right here, though, actually, I guess we do. I'll explain why in a moment. And that's just so that we don't hit the overrun. And right here is the other really key point. I now want to watch bit value 3. So I'm going to make it so that whenever bit 3 changes state, so that's from off to on in this case, I'm going to go call an interrupt. That will be able to get us out of this sleeping CPU mode. So the idea is the code is going to go execute to here, and then it's going to release the pin, and then once the pin rises above the threshold, whatever that is, I don't happen to remember it, it's going to go continue executing. Until then, the CPU will remain halted. The only way out of this will be to execute this code right here in PCInt1, and this is where I look at the time and set it to the local value TR. So let's just, for the sake of right after that, I'm going to set J equal to TR. The reason you do this is to make sure that nothing else happens anywhere else in the code that could taint the value. So let's give this a shot. I'm going to go run this now. Ah, excellent. So now what's going on is it's starting the stopwatch. It's setting up all the stuff that we talked about. It's putting the CPU to sleep. Then 27 to 28 time units later, it crosses that threshold and continues execution and reports the number back to me. So this is great. Now, if we look on this computer screen here, if I press and hold the button, the number increases. Only annoying thing here is it can wrap around. So if I press harder, 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 it will eventually wrap around to 0, 1, 2, it's not acceptable. Additionally, there's another problem where if I grab hold of the lead here, I can cause it to completely trip out. And that's because by making contact with it, I'm just collecting all sorts of interference from the room, and the value on that pin might not hit anything suitable for quite some time. As you can see here now, it's completely out of sync. Everything just fell apart, so I'm going to have to go kill it. The way around this is to set a max time. And so what we'll want to do is we'll want to have another interrupt here. So whenever comp A gets hit. Now, comp A, right here, I'm going to enable the interrupt for comparator A. What that's set to is 0xF0. So, if this timer ever reaches 0xF0, which is, I don't know, 248 or something, then it will go cause an interrupt. So, right here, now, the sleep CPU could either be triggered by the PC interrupt, the pin change interrupt, the pin going past that threshold under normal operations, or by timing out and being hit by the timer on this compare A value here. Either way, we still want to kind of set up the TR to be 0xF0 so that we know what it is. That way, we don't have to ever worry about going and looping around and then not knowing what value we really are at. So let's try that. Okay, still 27, 28. Now if I grab hold of it, oh, something's not quite right. Let's see what I did wrong. Huh. See, we're enabling the interrupt for that there. Perhaps we shouldn't be waiting as long there? Let's try that. Let's see. Ah, perfect. Okay, the problem was that we were waiting just absolutely too long. And also on the scope, we can see something interesting now. Remember how I said the value was up there? Turns out it's much, much lower than I originally expected. So that's why I can press and hold and it takes longer, longer, longer until it gets up to that other value. I think there's also some AC coupling here, so we might be seeing some of that. But as you can see, if I touch it right here on the pad, the value will go all the way up to F0, and there's really nothing much I can do electrically to mess it up and cause it to go on forever or loop around or do any other confusion. So we have just about everything that we need to do. Now there's a problem. This right here takes a certain amount of time to reach that even when nobody's touching. So we're going to need to calibrate that out. And the way we can do that is simply by running this code a couple times and then setting a calibrate value. So unsigned short calibrate equals 0. Unsigned char 0. So what I'm going to do is run for a couple cycles, and I'm going to say calibrated ++ if calibrated is less than 10, maybe. I'm going to increase that. And I'm not going to update j equals tr until it is calibrated. So else j equals tr. So now, until this loop is run for 10 times, we're not going to actually set this value here. Now what we do need to do is we need to say the calibrate is equal to tr. So that means after the 10th iteration through here, every time, it's going to be writing the value that it's currently on to this calibrate value. After the 10th time, it's going to say, okay, we're not doing that anymore. But here, if nothing has changed, the value in tr should be the same as the value in calibrate. So I should be able to subtract out calibrate. Now, this is a little bit annoying because I'm going to have to detect if j is greater than 0x(f)(0), j equals x0. The reason we have to do this right here is, if it's fluttering, as in we had before 27 and then 28, we're going to want to have that be, say, if calibrate happens to be 28 and tr is equal to 27, 27 minus 28 is a really nasty value, something we can't get. So what I'm going to do is I'm going to say if it's going to be one of those nasty values, because we can't have anything greater than f0 because of that timeout, I'm just going to say it's 0, don't worry about it. So let's give this a shot. Excellent. It's right now reading 0. So if I get my finger close, you can see it's reading 1, 2, 3, 4, 5, 6, 7, 8. And then if I press and hold C8. So that means that the calibration value was relatively medium, high. And I guess you could probably assume that it's F0 minus C8 would be whatever the current calibration value is. Let's do one more kind of interesting thing here. So right now we have TCR1 running at whatever they are, the 0, 1, or 1, 0, and 2, 1. So it's dividing it, and it's going very slow. I'm going to go a little bit faster now. So now it's really, really sensitive. If I get my finger even close to here, I don't even really have to make contact. As you can see, I'm not making contact, and it's registering just a little bit. So you can get this pretty detailed, but the problem is that you'll quickly run into no more room. You'll time out, because we only have an 8-bit timer here, before you actually get the data you're looking for. So right here, after trying to switch to 1, 0, or I guess it'd be 1, 1. Let's try that. Yeah, even with 1, 1, we still just don't have enough value. We can't go long enough in order to get any kind of good data. So yeah, this has been my my little touch sensor thing here. I hope you guys liked it. This has been the first time I've tried to do a Let's Code and Let's Learn together all in one video. And if you guys do like these, please tell me. Please keep telling me, because it's a lot more work than I'm used to putting into my videos. But if you guys like it, I will keep making them. Thanks for watching, and don't forget to subscribe if you haven't already.